Traditional arc welding pushes an immense, continuous thermal load into a workpiece. As the metal melts, a massive heat-affected zone radiates outward, threatening the structural integrity and dimensional accuracy of the surrounding material. Laser beam welding operates on a completely different principle. It applies a sharp, intense light beam to form a perfectly localized microscopic molten pool that solidifies in milliseconds, leaving the adjacent metal completely unaffected. This is a non-contact fusion process. By focusing light, it achieves extreme power densities on the order of 1 megawatt per square centimeter. It accomplishes this fusion while breaking several conventional rules. It operates without shielding gas, without the application of external pressure, and entirely without physical electrodes. To understand how electrical energy is transformed into this highly disciplined thermal tool, we need to strip the machine down and build a laser welder schematic from first principles. The core of the system is the active medium. In a solid-state laser, this is a neodymium YAG or ruby rod, known as the lasant. We surround this rod with high-intensity flash lamps, pumping massive pulses of electrical energy directly into the solid-state rod. This whiteboard sketch illustrates the quantum mechanics inside that rod. As the lasant material absorbs the pumped energy, the electrons orbiting its atoms are destabilized, excited to a higher energy state, labeled E3. When they inevitably drop back down to a lower, stable energy level, E2, they emit the difference in energy as quanta, or individual photons. This exact mechanism, stimulated emission, guarantees the resulting light beam is monochromatic. We have successfully converted raw electricity into organized light. But in this initial state, the light lacks the power density necessary to melt metal. It requires immediate and drastic amplification. Returning to our schematic, we see how the system captures this light. By placing a 100% solid reflector mirror at the rear of the rod and a partial reflector at the front, we create an optical cavity. Inside this resonator, the emitted photons bounce back and forth through the lasant rod at the speed of light. Each pass stimulates the emission of even more photons, rapidly multiplying the beam's intensity. The cavity acts as a threshold. The photons continue to bounce and build energy until the beam reaches a critical intensity, allowing it to finally breach the partial reflector at the front and exit the device. This optical cavity takes disorganized, low-power light and organizes it into a coherent, high-energy stream ready to be delivered to the target. Once the beam escapes the resonator, it is directed by flat optical mirrors toward the workpiece, where it strikes a final focusing lens assembly. These optics take the raw, wide beam and converge it down to an incredibly dense spot, typically measuring between 0.1 and 1 millimeter in diameter. To maximize weld penetration, operators apply a specific geometric rule. The focal point is not set flush with the surface of the workpiece. Instead, the optics are aligned so the beam reaches its narrowest point slightly below the surface of the metal. This schematic details exactly what happens when that focused beam strikes a joint in an overlap welding configuration. In transmission welding, the laser beam passes entirely through a laser-transparent upper material. The light is absorbed exclusively by the lower material, heating it directly. That lower layer then conducts the heat upward, melting both materials simultaneously to form an internal joint. The energy path from the flash lamp to the workpiece is complete. We can now fuse materials from the inside out, bypassing the external surface destruction associated with traditional welding. Looking at the completed architecture of the solid-state laser welder, we see a system purposefully designed to keep heat input extremely close to the absolute minimum required to fuse the metal. Because the process relies entirely on light rather than physical contact, thermal distortion is tightly constrained, and the physical tool wear that degrades traditional welding equipment is completely eliminated. Furthermore, the absence of physical electrodes guarantees that no foreign material or electrode contamination can enter the weld joint during the fusion process. Geometrically, the system offers extreme flexibility. Because the beam is steered exclusively by mirrors and lenses, it can be focused and aligned into highly restricted spaces where bulky, traditional welding heads simply cannot reach. By replacing brute thermal force with rigorous optical engineering, laser beam welding provides an uncompromising tool built for high volume,